Section 15.4, calculating enthalpy change. All of you guys, you know that diamond is made up of carbon. The same thing, graphite is also made up of carbon. Diamond, over a time period of millions and millions of years, will break down into graphite. Now, converting diamond into graphite will release energy. How much heat is released when a diamond changes into graphite? Can we measure this amount of heat using a calorimeter? The answer simply will be no, we can't. Sometimes it's either impossible or impractical to measure the delta H of a reaction by using a calorimeter, for many reasons. Some reactions, as we said, they occur slowly, like converting diamond into graphite. Other reactions, they occur under conditions that are difficult to duplicate in a laboratory. Still other reactions, they produce products other than the desired one, such as the formation of the sulfur trioxide. It produces, in addition to sulfur trioxide, it also produces sulfur dioxide, SO2. Now, for these reactions, chemists, they use a theoretical way to determine the delta H. They use the Hess law. Hess law states that if you can add two or more thermochemical equations to produce a final equation, again, if you can add two or more equations to produce a final equation for a reaction, then the sum of the enthalpy changes for the individual reactions is the enthalpy change for the final reaction. How can I use this law to measure or to find the delta H of a certain reaction? Let's take the formation of sulfur trioxide. How can I use Hess law to find delta H of this reaction? First of all, as we said, we should have chemical equations that contains the substances. They should contain sulfur, they should contain also oxygen and sulfur trioxide. These equations, they should also with a known enthalpy change. So we have here two equations that includes all the three substances in the reaction. The first reaction is sulfur solid plus oxygen produces sulfur dioxide. The second reaction is sulfur trioxide decomposes into sulfur dioxide and oxygen. Both of them, they have delta H. Now, Hess law states that the sum, if the sum of two or more than two reactions produces a final equation, so the delta H of the final equation is simply the sum of the delta H's of these two or the individual reactions. But we can't just add them. We have to follow some steps. The first step, we should organize the given reactions where the total effect yields the reaction needed. If you compare the desired reaction with these two reactions, you will find that sulfur, here we have 2 moles of sulfur, or next to sulfur there's a coefficient 2. Here there's just 1. So we have to multiply the whole equation with 2, even the delta H. So the reaction will be like this. Now, the second reaction, the sulfur trioxide, it's a reactant, while in the desired equation sulfur trioxide, it is a product. So we have to reverse or flip the equation. So when we reverse the equation, we have to change the sign of the delta H. Now we can add. After we organize the equation, the chemical equation, and they will yield exactly the reaction that is needed. Now, after doing that, we can just add up the equations. Make sure to cross or to eliminate the terms that are on both sides, the like terms on both sides. If there's like terms on the same side, we add them up. If they're on opposite sides, we cancel them. Here, the SO2 and the SO2, they are on opposite sides. One in the reactant, the other in a product. We can cross them. We have here 2 and here we have 2. While oxygen, both here and here we have oxygen, they are on the same side. Both of them are reactants, so we add them up. it's 2, and 1 here, it will be 3 oxygen. And finally 2 SO3. What should I do with these delta H's? As we said, we just add them up. The answer will be negative 792 kilojoules. Let's consider another example. Use thermochemical equation A and B below to determine the delta H for the decomposition of hydrogen peroxide, H2O2. This is the desired equation, and we have two thermochemical equations given with their delta H. As we said, we have few steps to follow, 3 steps. Step number 1, we organize the equation. How? By either reversing if needed, or multiplying by a constant number, or sometimes both of them. Even in some cases, we don't change the equation. Then after doing that, after organizing the equations, we can add them up, and finally we add the delta H of these reactions to find the delta H of the desired equation. So starting with equation A, if you compare the equation A with the desired equation, you will find that the H2O water here, it's a product, and in equation A it is also a product. Here we have 2 moles, and here we have 2 moles. So equation A, we keep it simply the same. As you can see, even delta H stays the same. Now equation B, the hydrogen peroxide in equation B, it is a product and you have just 1 mole, while in the desired equation we have 2 moles of H2O, and the H2O, it's a reactant. So in this case we have to do 2 steps for the same equation B. We are going to reverse it, and we are going also to multiply it by 2. So the equation will be in this form. Now the equations are ready, we organize them. We will go to the second step. The second step, we add the equations. As we said, if you have a substance on both sides, we cross them, we cancel them, we eliminate them. If they are on the same side, I mean by that, in both reactants or both products, we add them up. So H2 first, hydrogen gas. We have 2 hydrogen gas on the left side, while here we have on the right side, they are opposite sides, we cancel them. H2O2, there's no other term in the product, so we keep it the same. H2O, water, keep it the same. O2, we have here 1 on the left side, 1 on the right side. Here we have 1 mole, here we have 2 moles, so we just subtract them. It will be, or the remainder will be 1 mole of O2. It's the same like the desired equation, exactly the same. When we finish adding them up, we simply add delta H. The answer will be negative 196 kilojoules. So Hess law allows you to calculate the unknown delta H values using known reactions with their known or experimentally determined delta H value using the calorimeter. Now, recording delta H values experimentally for all the non-chemical reactions, it is a huge and unending task. Instead, scientists, they record and use the enthalpy changes for only one type of reaction. It's the formation reaction, the formation of a compound, 1 mole of a compound from its elements in their standard states. When I say standard state, I mean by that the state at 1 atm and 25 degrees Celsius. For example, the standard state of iron at 1 atm and 25 degrees Celsius is solid. The standard state of oxygen is gas. The standard state of water is liquid. The standard state of bromine is a liquid, and so on. So a reaction in which the compound is formed from its elements in their standard state, and the delta H of such a reaction is called the standard enthalpy of formation of the compound. Now, take this example, the formation of 1 mole of SO3. It's a compound, it's formed from its elements, and these elements are in their standard state. The sulfur is in solid state, which is the standard state, and the oxygen is in gas state. So the formation of 1 mole of a compound from its elements in their standard state, the delta H of this reaction is called the standard heat of formation, delta H formation, which is in this case negative 396 kilojoules. From where we get this this value, this delta H? First, we have to keep in mind this note. Guys, to measure the height of a certain mountain, we always measure it relative to a point of reference, which is in this case the sea level. Above the sea level, it's positive. Below the sea level is negative. We will use a similar idea in calculating or determining the standard enthalpies of formation. We have an assumption here. The assumption is the elements, any element in its standard state, the delta H formation is 0. Based on this assumption, we can find the delta H formation for the compounds. For example, the formation of 1 mole of NO2 or the formation of 1 mole of SO3 gas. The NO2 gas is formed from nitrogen gas and oxygen gas. To produce 1 mole of NO2, 33.2 kilojoule is required. Because the delta H of formation of these elements is 0, they are the reference point as we said. So this amount, it will be the delta H formation for NO2 gas. The similar thing for sulfur trioxide. Sulfur trioxide is made up, the elements are oxygen and sulfur. The standard heat of formation for oxygen and sulfur in their standard state is 0. When these two combine to produce again 1 mole of SO3 gas, it will produce negative 396 kilojoule. This delta H or this heat change is called the delta H formation for SO3. This table, guys, shows different substances with their delta H of formation. As you can see here, bromine liquid is not like bromine gas because standard state for bromine is 0. The similar thing for iodine. The standard state for iodine is solid. If you change it into a gas, the delta H formation is above 0. And so on. The similar thing for other substances. These delta H formation for the compounds can be used to find delta H of a certain reaction. How we apply this formula? The delta H of the formation of a certain reaction is equal to the sum of the delta H formation of the products minus the sum of the delta H formation of the reactants. Again, products minus reactants. Let's take this example. Here we have, suppose you want to calculate delta H reaction for a reaction that produces sulfur hexafluoride. We have H2S for Fe, for F2 I mean, produces 2 hydrogen fluoride plus sulfur hexafluoride. Now, how we can calculate delta H formation for the reaction? As we said, we apply the formula. It's the sum of the delta H formation for the products in these two minus the delta H formation of the reactants. But we have an important note. Don't forget to multiply each delta H formation by the coefficient in the equation. Here, delta H formation of the HF is the product. We start with the product first, then the reactant. We multiply it by 2. This one we don't multiply it by 2, just by 1. You know, the coefficient is 1. Minus, but again, the sum, we put plus between them. Minus the delta H formation for the reactants, their sum. Okay, here we have just 1, here we have 4. So this one, we don't multiply it, you just multiply by 1 actually, or keep it the same. This one, we multiply it by 4. Using the table, we can use the table to find the delta H formation. For the HF is negative 273, for the SF6 is 1220 negative, and so on. Just substituting the values, you are going to find delta H for the whole reaction, using again the delta H formation for the compounds. Now, let's consider another example. Use standard enthalpies of formation to calculate the delta H for the combustion of methane. CH4 gas plus 2O2 gas produces CO2 gas plus 2H2O liquid. To calculate the delta H of the reaction, we have to use the formula. Delta H of the reaction equals the sum of the delta H of formation of the products minus the sum of the delta H formation of the reactants. The products here are CO2 and H2O. CO2 in the gas state, H2O in the liquid state. So carbon dioxide, it's this one, and water is this one. These are the values. For CH4, this is CH4 gas, and O2 gas, it's here. This is the value, it's 0. So we just substitute the values, and as we said, we add the delta H formation of the products together and delta H formation of the reactants together. Don't forget to multiply the delta H of formation by the coefficient. So here, the delta H of formation for CO2, it's the product plus that of the H2O, which is also a product. We add them together minus the reactant. Here, the delta H formation of the H2O multiplied by 2. Here, the coefficient is 1, so just keep it the same. For the reactants, CH4 has coefficient 1, so keep the value the same, while O2 multiplied by 2. It has a coefficient 2. The delta H formation of oxygen gas, it's 0. For that, CH4 is -7.5. For water is -286. And for CO2 is -394 kilojoules. I round these numbers. So we just, after substituting the values and of course multiplying them with the coefficients, we just solve normally to get the delta H of the reaction, which is -891 kilojoules. So again, this is how we find delta H of the reaction using the standard heat of formation for different substances. Thank you for listening.